Okay, good afternoon. Take some time to write down the title of the lesson, and then I'll talk about a couple of things to start with, and then more to the point of what this lesson will contain and what chapter 5 is all about. So today we start chapter 5, which is about solving linear programming problems in any number of variables. That is the goal. So same type of problems that we dealt with in chapter 4. We have objective optimization problems in which you have an objective function and some number of constraints given by linear inequalities. Now, unlike in chapter 4, we focus now on problems with any number of variables and constraints. So in other words, we cannot necessarily use in general, we cannot use the graphical method, because if you have 3 or more variables, that's either very difficult in 3 variables or impossible in 4 variables and more, because you don't have a physical representation of the feasible region. So the solution of the system of inequalities cannot be represented by drawing on the plane like we did it so far. I want to point out that the algorithm involves, at the end of the day, row operations. So the mechanics of how you actually come up with the solution are very similar to what you guys did when you solved linear systems using Gaussian elimination. That is the good news, right? So all you do at each step, you will basically create some ones in various positions using row operations, and then zeros above that one and below, using again row operations that you're familiar with. The big difference, and we should even write it down as a remark here, that the algorithm that we're going to learn requires a very precise arrangement of the equations. And very specific steps. So you still use row operations, but you don't have as much flexibility as you had when you solve linear systems with the Gaussian elimination in terms of how you create those zeros and how you switch the rows and so on and so forth. So it's a much more rigid algorithm. And for that reason, we're going to spend lesson 5.1 in learning how to arrange the problem in that specific form, and also how to perform the computational step, if you want, that you have to perform several times repeatedly in the algorithm, the so-called pivoting operation. So the pivoting operation is the computational step in the algorithm. But before we get to that pivoting operation, the most important thing is to learn how to arrange the problem in the required form. So I'm going to actually talk about the algorithm itself in lesson 5.2, and I will start actually by showing you what the algorithm does. The proof of the algorithm, the explanation why the algorithm gives you the maximum or the minimum of that problem. I won't get into it because it's beyond the scope of this lesson, but I will show you with a visual example. So I will apply the algorithm to a graphical problem to see what it does at each step when you perform this pivoting operation. So again, hold your horses so far, in the sense that it may not make sense in the beginning why we do the things we do. Let's focus on, like I said, on how you arrange the problem in the so-called standard form. And then the so-called Simplex Tableau, which is the associated matrix. Another important remark is that we're going to talk about first how to solve maximum problems in standard form. So the maximum problem needs to have a specific format. If it doesn't have that format, or if it cannot be written in that format, again, I'm not going to cover this in this course. I might add an optional video for those who are interested in, but that's not going to be part of the exam. So we're going to focus primarily on the maximum problem in the standard format. So the standard form description is actually very simple. So standard form, so maximum problem in standard form means that the problem needs to satisfy two conditions. So the first condition is that all constraints are less than or equal to a positive number. And the second condition is that all variables are non-negative, meaning that x1 is greater than 0, x2 greater than or equal to 0, x3 greater than or equal to 0, so on and so forth. So depending on how many variables you have, all of them should be non-negative, which is what happens usually anyway in many word problems. So let's, on this page, let's give a couple of examples of problems in standard form and not in standard form. So suppose, for example, that we have x1 minus 3x2 plus x3 less than or equal to 10, x1 minus 5x2 plus x3 less than or equal to 5, and these are the constraints, and let's say the objective is to maximize p equals 5x1 minus or plus 2x2 and plus x3, let's say, right? So that's the function to maximize. So obviously it should be linear, because otherwise we can talk about the simplex algorithm. And notice that this one is in the standard form. So all constraints are less than or equal to a positive number, and all variables, like I said, are positive. Just want to see one quick examples. All right. So I was looking for the example that I want to do later. Another example, so this is in standard form. On the other hand, take a look at the following two examples. So let's say this is 1 and the other one 2. Suppose you have 3x1 plus x2 greater than or equal to minus 3, x1 plus 5x2 less than or equal to 7. And then I want to maximize p equals 10x1 plus x2. Leave some room over there and write another example here. So let's say the constraints are, let's put 4 variables this time. x1 plus 2x2 plus x3 plus x4 less than or equal to minus 2, x1 minus x2 plus x3 plus 2x4 less than or equal to 10. And let's say I want to maximize the function p equals, let's say, x1 plus x2 plus x3 plus x4. So these are all versions of linear programming problems, right, in which the constraints, like I said, are inequalities and the objective function is linear as well. So if the problem is not already in the standard form, like we have this one, the first one that I mentioned here, the question is whether it can be written in the standard form or not. So remember, there are only two conditions to establish, right? That all constraints are less than or equal to a positive number, right? So this one satisfies that condition in the first example. Now, if I look at the second example, obviously the first condition doesn't satisfy the constraint. I mean the condition less than or equal to a positive number. But I can change it to look in the standard form by simply multiplying the entire inequality by -1. Remember, if you multiply an inequality by a negative number, then you reverse the inequality sign. So if I multiply by -1, that's going to be minus 3x1 minus x2 less than or equal to 3, x1 plus 5x2 less than or equal to 7, and then we need to maximize p equals 10x1 plus x2. And now this is in standard form. So it is in the standard form to begin with, if you think about it, in the sense that if it's not already, I can write it in the standard form by simply using a simple algebraic manipulation, namely multiplying the inequality, the first inequality, by -1. So be aware for this type of situations, because sometimes the problem is not already given in the standard form. On the other hand, some problems are not at all in the standard form, nor can be brought in the standard form. If you look at this third example, if you do the same trick, so this one, the first inequality is less than -2, so it doesn't satisfy the condition. If you multiply by -1, again, that reverses the inequality sign. But you still do not have the problem in the standard form, because there are in fact two conditions, right? All constraints are less than or equal to a positive number. So you need to have less than positive, less than positive, less than positive. Same thing on example 2. Example 3, no matter what you do, you don't get the constraints in terms of less than a positive. If I multiply, if it's in this form, is less than a negative. If I multiply by -1, it becomes greater than a positive. Either way, this cannot be brought in the standard form. And this is the type of problem that I won't require in the exam. And like I said, later on, maybe when I'm done with the other lectures, I might add a video lecture just to show you how you actually deal with problems like this. There is a modification of the algorithm which deals with problems like this, but again, I won't get into it right now. So once we establish how the problem looks like in the standard form, now comes the more important part. How do you actually arrange this into a system and then the augmented matrix? Because there is another procedure to perform before you actually start the algorithm itself. So stay tuned for the second page. Okay, so like I said before, let's suppose we have a maximum problem already in standard form. We're going to perform a couple of modifications until we bring it into what we're going to call later the initial simplex tableau, which is basically a fancy augmented matrix of a system of actually equalities. You will see how we're going to end up with equalities, in fact, before we proceed with the algorithm itself. So the simplex tableau is basically the initial matrix associated with this algorithm. So let's start with an example like before. So suppose the constraints are 2x1 plus 2x2 plus 3x3, and that's less than or equal to 5. And then x1 plus 2x2 plus x3 less than or equal to 10. And let's say the objective is to maximize the objective function p equals 5x1 plus x2 plus 3x3. All right, so the first thing you do is to change these conditions into equalities by introducing the so-called slack variables, which we're going to denote by S1, S2, S3, depending on how many you need in general. And then another thing is to write all the terms in the objective function to the left side. So please pause, take a moment to actually write down in words. We're going to write in words just once, because then after that we're going to just follow our examples. And all of these steps are also given in a formula sheet, which I'm going to point to later. But this is the first thing, okay? So let me illustrate what the slack variables mean essentially. And you'll understand why this ties up actually with the so-called standard form. I mean, why we need that condition to begin with. So we need to change the conditions into equalities, right? I mean, all inequalities should become equalities by introducing slack variables, which will denote S1, S2, S3, and depending on how many you need. And then write all the terms in the objective function to the right side of the left side of the equality, right? I mean, we're going to move those terms 5x1 plus x2 plus x3 to the left side of the equality. The slack variable, imagine the following. So you have a quantity less than 5. Let's look at the first condition. To make it equality, you need to add stuff on the left, right? I mean, stands the reason that if you want to make an inequality from less than something positive, you gotta add like a positive quantity, which will denote by these slack variables. So for example, 2x1 plus 2x2 plus 3x3 is gonna need another quantity, positive quantity, let's call it S1, to bring it up to 5. So that's how you can interpret essentially the role of these slack variables. Add what's missing to make it equality. So we want basically to change the system into the constraints into a system of equations. And we have to choose different slack variables because the left side of all of these constraints is different. We can't use the same one. By the same token, x1 plus 2x2 plus x3, to make it up to 5, obviously we need to add some positive quantity, and that'll make it equal to 10. And then we're going to move all the terms to the left. Why? Well, again, that's all about how this algorithm is implemented, but it's about essentially standardizing these steps, right? So the last equation will always be the objective equation with all the terms moved to the left side. Let's actually arrange it by the column like that. So p minus 5x1 minus x2 minus 3x3 equal to 0. I mean, I arranged it like that because I wanted to have these coefficients of x1, x2, x3 on top of each other, although that's not strictly necessary. So this is the system that you obtain from the original problem in terms of these slack variables and these equalities essentially. And the next step is to simply write the augmented matrix. So from this point on, we're going to write the augmented matrix with one additional column on the left called the column of the basic variables. Also abbreviated by BV, which are the variables corresponding to the identity matrix column. Again, it will be much more sense. It'll be much more meaningful once you actually see how the matrix looks like. So let's carefully write down the augmented matrix. The very important thing is that this augmented matrix, so the order of the columns is P x1, x2, x3, s1, s2. So it's very important to write the column of the augmented matrix with the variables in this order. So always the objective function, P, right? P is a variable essentially in this system, then the columns of x1, x2, x3, however variables you have, and then the slack variables. So the order of the columns in this matrix is always the objective function, the variables, the original variables in the problem, the slack variables. Okay, so if you do this correctly, let's arrange it nicely here. So we have the first coefficients are 0, 0. I'm going to write the matrix by column, right? So I mean corresponding, in fact, let's actually write down the first row just to indicate clearly what are the, and we're going to leave the basic variables toward the end, right? So we're going to have the column for P, then for x1, x2, x3, slack variables s1, s2, and then the right hand side of the system, which I'm going to label it like RHS. So this stands for the right hand side of the system. Later on you can skip these labels if you know what you're talking about, but in the beginning go slow and make sure you arrange it nicely like that. So I'll get back to the basic variable column immediately, but the coefficients of P, now look up to the system here. So we have 0, 0, 1. That's always the case in the beginning, right? So there's no P on the first equation, no P on the second equation, so the coefficients are 0, 0. And then there's P on the last equation with the coefficient 1. Look at now at the coefficients of x1, 2, 1, and minus 5. Then the coefficient of x2, that's going to be 2, 2, and minus 1. And then 3, 1, minus 3 for x3. Now pay close attention. S1 is on the first equation, so its coefficient is 1, and it's missing on the other equations. There's no S1 in the second, there's no S1 on the last equation. So of course, the variables are 0, 0. I mean, the coefficients are 0, 0. No S2 in the first equation, that means coefficient is 0 over there. S2 on the second equation, we have 1 over there. There is no S2 on the last equation, therefore the coefficient is 0 on the last one. And then the right hand side column, which is 5, 10, and 0. So once you write a simplex tableau, draw a couple of more lines that isolate the last and the first column and the very last row, because there will be important information that we're going to extract from these columns, the first and the last one and the last row. So as I mentioned before, what we're going to call basic variables, so go back to this description here, what I called basic variables. These are the variables corresponding to the identity matrix column. So if you look carefully, you always have the columns of the identity matrix. In this case, the 3 by 3 matrix. So we have 1, 0, 0, 0, 1, 0, 0, 0, 1. So you always have these columns, not necessarily in that order, keep in mind, but you will have these columns in the simplex tableau. What we're going to call the basic variables are the variables corresponding to these columns in this order. So in the beginning, notice that S1 corresponds to 1, 0, 0. So that gets to be the first basic variable. Write it on the left. S2 corresponds to 0, 1, 0. This gets to be the second basic variable. And finally, P corresponds to the column 0, 0, 1. And therefore, the last basic variable is P. And in fact, P is always basic variable, because the other basic variables will change as the algorithm moves along. So in the process of the algorithm, you also have to keep track of the basic variables. Once again, once you do the computation that you will do later, these basic variables will change, so you have to keep track of them again in this order. You're looking to see which one is corresponding to 100, 010, 001, and so on and so forth, because the size of this identity matrix depends on the number of variables and equations you have to begin with. So this is what we're going to call the initial simplex tableau, the starting point of the algorithm, which we will discuss in the later portion of the course. I mean the second section, after this section. So another important piece of information that we have to deal with in this class is the so-called pivoting operation. The main ingredient in dealing with this algorithm is to do the so-called pivoting operation. This means choosing one specific entry. It's not going to be a random choice. We will have a specific way to choose it. So one of the entries is going to be a pivot. So we're going to choose one entry called a pivot. The way we choose it, again, we're going to see later. And we're going to do the pivoting operation, which consists in the following. So pivoting operation entails the following. You're going to divide the pivot row by the pivot to make it 1, basically. So you create essentially a 1, just like you create leading ones in the Gaussian elimination. So divide the pivot row by the pivot, and then create zeros above and below the pivot using row operations. And the pivot row. So basically, you'll have to use the pivot row to create the zeros above and below. So it's much more rigid algorithm. Again, you will see it later. You can't just use any rows as you wish to come up with these zeros. You just have to use the pivot row once you choose the pivot in a specific way. And I'll show you actually how the pivoting operation works. How we can do that in an example, and of course more will come later. Right, so you had basically the pivoting operation is basically 2 steps: dividing by the pivot, and then the creation of the zeros above and below the pivot using the pivot row. So let's stay tuned for the next page to show you how the pivoting operation works, and maybe we're going to end up with another example. Okay, so we're going to illustrate how pivoting operation works. I just wrote again the Simplex Tableau to begin with before. In the previous page. So the pivot is going to be 3 in this case. Again, we'll talk about in the next lesson why that's the case. So let's do the 2 steps involved in the pivoting operation. So the first thing is to make the pivot 1 by dividing the row by the pivot. So notice the algorithm is very rigid. You can't make 1 instead of 3 by any other means besides dividing the pivot row by the pivot value. So in this case, you just divide row 1 by 3. And let's copy the whole matrix. Later on, you can skip this labeling until the end just to speed up. But for now, let's take our sweet time in doing this. So S1, S2, and P, that's the column of the basic variables, which will change later as you will see. So for now, the only thing that modifies is row 1, because we divide row 1 by 3. So 0, 3 over 3, which is 1, 1 over 3, 1 over 3, 1 over 3, 0 over 3, which is 0, and then 5 over 3. And then for now, the other 2 rows stay the same. There's also another method in which you do the pivoting in 1 step. but I would advise you to do that later. I'll show you later that shortcut. For now, let's do it in 2 steps. So now the pivot became 1. Don't lose track of its position, right? Because it's the same position. So the first non-zero entry of the first row happens to be the pivot in this case. Okay, so the next thing is to make zeros above or below the pivot. Since the pivot is on the first row, we only do zeros below 1, and we must use row 1 in doing these pivots. So that means you need to subtract row 1 from row 2 and change row 2. And then we need to multiply row 1 by 5 and add it to row 3, and we're going to change row 3. So we can make zeros below the pivot. So let's see how the matrix changes under these operations. And then I'm going to leave empty for now the boundary value, excuse me, not the boundary, the basic variable column, because you will see the basic variables will change after you complete the pivoting operation. So let's copy the first row. And here we may have to use some scratch papers because we have fractions, which we can't really avoid because each step is really fixed. You know, I mean, we have to use the pivot row. So whether we have fractions or not, that's besides the point, right? We have to do the operations according to the algorithm. So we have minus row 1 plus row 2, right? So it's going to be 0 minus 0, minus 1 plus 1, or row 2 minus row 1, 1 minus 1 is 0, 2 minus 1/3. So I'm going to write it here. That's going to be 6 minus 1 over 3. That's 5 over 3. So this is 5 over 3. The next one is also 2 minus 1/3. So it's still 5 over 3. Then it's 0 minus 1/3, which is minus 1 over 3. And then 1 minus 0, which is 1. And then 10 minus 5 over 3, which makes it 30 minus 5 over 3. And that's 25 over 3. All right, so moving on now to the last row. Now we do 5 row 1 plus row 3. 5 times 0 plus 1 is 1. 5 times 1 minus 5 is 0. And then 5 times 1 over 3 is 5 over 3 minus 1. That ends up being 5 minus 3, which is 2 over 3. Let's see, then it's 5 over 3 minus 3. 5 times 1 over 3 minus 3. That's 5 minus 9 over 3. Again, you may pause and take your time with this computation. So minus 4 over 3 is the updated entry there. 5 over 3 minus 0, that's 5 over 3. And then 5 times 0 plus 0 is 0. And then finally, 5 times 5 over 3 plus 0, that's again 25 over 3. All right, so notice, again, pause if you want to catch up with the computation, but once you do that, notice the basic variables changed. So now the first column of the identity matrix is corresponding to x1. So it's very important to update the basic variables correctly. Very important, because you see the answer at the end, when the algorithm ends for the maximum and minimum problem, you gather the information from the basic variables and what you have on the right hand side column, as you'll see later. So previously 100 was corresponding to S1, which is the reason I wrote S1 here in the initial Simplex Tableau. Now 100 is corresponding to X1, so the first basic variable becomes X1. Second basic variable remains S2, and then P is still the same. In fact, P is always, I think I mentioned this already, but that's okay, it's always a basic variable throughout this process. We also have what we called current values of the variables. And the idea is that at each step in the Simplex Tableau, so if a variable is a basic variable, so if it is a basic variable, its current value is on the right hand side column. If it's not basic variable, so if not basic variable, then its value is 0. Okay, so this is how the algorithm is set up. Current values are on the right hand side for the basic variable. If they're not on the right, if they're not basic variables, automatically the value is 0. So for example, here on the initial Simplex Tableau, S1 current value is 5, right, the right hand side. S2 current value is 10. P current value is 0 because that's the right hand side. And X1, X2, X3 are all 0 because at this point they are not basic variable. So notice that the current value of P and the current value of X1, X2, X3 should be in agreement because they come from the objective function. So if you plug in this into the objective function, it should be in agreement, right? I mean, the objective function in this problem was, I think, what was it? 5x1 plus x2 plus 3x3, right? On the other hand, after pivoting, now the current values are the following. X1 now is a basic variable, so its value is to the right hand side, 5 over 3. S2 is a basic variable still, so it's 25 over 3. P is equal to 25 over 3. Right hand side, right? Basic variable as well. X2 is still not a basic variable. X3 is not a basic variable, so it's assumed to be 0. S1 is not a basic variable, so it's assumed to be 0. So remember, the objective function in this problem, like I said, was 5x1 plus x2 plus 3x3. And notice that the basic variables, or excuse me, the current values should satisfy the objective function. So indeed, if I plug in the value of x1, which is 5 over 3, plus the value of x2, which is 0, plus the value of x3, which is 0, you should end up with the current value of p, which is 25 over 3. Okay, so you can check this just as an extra step if you want to check to see your computation is correct. So in a nutshell, this is how the algorithm will evolve. You start with a simplex tableau associated with the problem, and you pick a pivot according to a rule we're going to talk about in the next lesson, and you perform the pivoting operation, which gives you another tableau. Then, depending on the case, you perform another pivot until you reach the solution, which is guaranteed to be reached after a several number of steps, depending on the case. I'm going to finish up with another example of choosing the initial simplex tableau in another pivoting on the last page of this lecture. So stay tuned. All right, so here's another example. And let's say we have this time 2 variables and 3 constraints. So we have x minus y less than or equal to 2, 2x plus y less than or equal to 4, x plus 2y less than or equal to 6, and we want to maximize p equals 3x plus y. Okay, realize that this is in standard form. Check the conditions. Inequalities less than or equal to positive numbers, all of them. And then I forgot to add, all variables are non-negative. And I forgot to mention that in the previous example. So assume that x and y are positive to begin with, like in, part of the constraints. To begin with, that you have the non-negative condition. So this time around, if you look carefully, you need 3 slack variables, because you have 3 inequalities to write as equalities. So you add S1 to make it equal to 2. You need S2 to add to make it equal to 4. You need another slack variable S3 for the last one to make it equal to 6. And remember, the last equation is the objective function written with everything on the left side. So move 3x plus y on the left side. And this is basically the system that you're going to start with and write the Simplex Tableau. Start with the basic variable column, followed by the P column, the variables in the system, x and y, the slack variables, and then the column of the right-hand side. So you see the number of columns and rows is not predetermined. It depends on the number of variables to begin with and the number of constraints. So any combinations are possible. And as always, once you write the coefficients, make sure you isolate the last row and the first and the last column with some straight lines. So let's write by columns the coefficients. Coefficient of P, the column of P, is always with all zeros except the last one, right? Because there's no P in the first three equations. And there's just P on the last one. So it's 0, 0, 0, 1. Coefficients of X, 1, 2, 1, and minus 3. Don't forget, make sure you don't miss any of these coefficients. Coefficients of Y, minus 1, 1, 2, and minus 1. And then the slack variables. S1 in the first equation, no S1 on the other one. S2 only in the second equation, S3 only in the third equation. And then the column of the right-hand side, 2, 4, 6, and 0. So, like I said, isolate the last row, and the first and the last column. Later on you can skip this, but now just be picky with these arrangements. All right, let's identify the basic variable. Very important to make sure you do this correctly. Identity matrix column, starting with 1, 0, 0, 0. So S1 is the first slack variable, S2, then S3, and P, always a basic variable. Notice that in the initial Simplex Tableau, you always have the slack variables as the basic variables to begin with. So the current values, well, obviously S1 is 2, S2 is 4, S3 is 6, P is 0, and both X and Y are 0 because they're not basic variables. Okay, as it turns out, once again, be patient. The reason will be explained in the second lesson. The pivot in this case is again the first one, although actually you can have a choice in this case, but let's choose this one, which is easier. I mean, there is no choice on the matter except with in some cases. This is the pivot in this case to choose. The first one, just like before. And pivoting operation means to divide the pivot row by the pivot to make it 1. We skip that part because it is already 1. So there's no change. All we got to do is to make zeros below the 1, the pivot, using the pivot row. So we're going to do minus 2 row 1 plus row 2. Then we're going to do minus row 1 plus row 3. And this will change row 3. And finally, we're going to do 3 row 1 plus row 3. 3 row 1 plus row 4. And that'll be my new row 4. And let's write down again the new Simplex Tableau. So obviously the first row stays the same, 0, 1, minus 1, 1, 0, 0, and 2. And then update the other row. So 0 minus 1 times 2 plus 2 is 0. Minus 1 plus 2 makes it 3. minus 2 plus 0 is minus 2. Minus 2 times 0 plus 1 is 1. And then minus 2 times 0 plus 0 is 0. And finally, minus 2 times 2 plus 4 is again 0. Minus row 1 plus row 3, 0. Excuse me. Minus 1 plus 1 is 0. Minus negative 1 plus 2 is 3. Minus 1 plus 0. Minus 0 plus 0. Minus 0 plus 1. And then minus 2 plus 6 is 4. Especially if you have many entries in each row, you have to be patient so that you won't make a mistake. Finally, the last row is 1. 1 times 3 minus 3. So I'm looking now at 3 row 1 plus row 4. That's 0. Minus 1 times 3 minus 1. That's minus 4. 3 times 1 plus 0. 3 times 0 plus 0. 0. 3 times 2 plus 0 is 6. And again, isolate the last row. New basic variables. Corresponding to 1, 0, 0, we have x as the basic variable. Then 0, 1, 0, 0, that's going to be the second basic variable. Then the third basic variable is still s3, just like before. And p is always the basic variable. This first column will never change throughout the process. So the current values, x is basic, so right hand side is 2. So x is equal to 2, s2 is 0, s3 is 4, p is equal to 6. The rest of them are not basic, so they are automatically assigned the value 0. And notice again how x and y and p are in agreement, coming from the objective function. So remember, the objective function was p equals 3x plus 6y. So 6 should be equal to 3 times 2 plus 0, which it is, right? You don't have to do this check, but just want to emphasize that the current values should obviously satisfy the objective function. To anticipate a little bit, this pivoting operation does nothing but checking each corner at a time. If you talk about a problem in 2 dimensions like this one. So I will illustrate this in the next lesson. And then basically what's left to do is to see how we actually choose this pivot and how we know whether we reach a solution, the maximum in this case, or not. But until then, practice as much as possible with writing the Simplex Tableau from a standard format, from a maximum problem in the standard form. And that's it for today.